In order to add let CC to Mo, we'll need a new kind of expression, let CC, which takes a symbol and an expression body. We also need to update values to have a new continuation value, cont_v, so that when we interpret a let CC, we can bind a symbol to a continuation inside the environment. We can see that binding in action over here inside the interpreter. So here's the case for let CC. We have a symbol n and a body expression. And the next step is to interpret the body in an extended environment where we bind n to the current continuation, k, and then carry on interpreting. The way to use a continuation is by applying it, just like a function. Over here inside the continue function, we can see that. So we have, in our application case, our match now has two clauses. One if we're applying a closure, and the second if we're applying a continuation. If we're applying a continuation, then we continue on with kv, the continuation inside of our cont_v value. And we ignore the current continuation next k. Let's look at the implementation. Here's the Mo lambda k interpreter extended with let CC. So now we have three kinds of values: integers, closures, and continuations. In our expression type, we have all the normal things plus let CC. Down below in the interpreter, we have the case that we saw before for let CC. And then inside continue for applications, we're looking for a continuation value. Now let's test it out. So all the tests that we have pass, but some of these are pretty interesting. So here's the first example using let CC. We bind the current continuation to k, and then we have 1 plus k applied to 0. So when we call k here, we jump out to the top to where k is bound. And so in the end, we just get 0 as the result. We forget about this 1 plus. Here's a more complicated one. Let f equals let CC k, k. And inside the body, we call f with fun x returns 10. When we capture k here and then immediately return it, we've got k is equal to this whole. K is equal to this continuation. Let f equals the whole, and then inside the body call f with that function argument. And then another way of writing this is let k is a fun that takes some function value and then swap that function value into the whole. And then on the next line, we're calling f with fun x10. Well, f is bound to k, so this is just like calling k with fun x10. And so we wind up swapping in, let's see, let f equals fun x10 in f applied to another copy of fun x10. And the overall result is fun x10 applied to fun x10. And that's how we get 10 as the result. Okay, one more. Let CC escape. Let v equals 1 plus let CC k escape k, fun a, v plus a. And then we apply this whole thing, let CC escape, to 2. So what's going on here is that escape is bound to whole applied to 2. Or in other words, fun, which is expecting a function value. And we apply that function to 2. Next, we see that v is equal to 1 plus let CC capture k, and then we immediately call escape with that k. K now is bound to a continuation. K is equal to the whole continue up until this point. So we're inside of an application. Let v is equal to 1 plus whole on a. And then we apply that to 2 at the end. And we can also think of k as a function that swaps in a value for the whole, in this case, a number value. But now right after we bind k, we call escape with k. So we jump back up to the top escape, and we've got some function k. When we jump to the top, we get back to this application. So we immediately call k with 2 as its argument. finding k, call k with 2. And that's because we called escape with k. So next up, that call k of 2, that steps to let v equals 1 plus 2 with the let body. So then v is equal to 3, and we wind up returning a function from the let body that has font a, 3 plus a. Good, so that's the result now of the left-hand side of k. So we jump back into where the hole was, we finished the let expression, we got back this result, function result, and now we apply that to 2. So we get 3 plus 2, and that's how we wind up with 5. This is pretty wild. With Let's See, we can jump back and forth across the program, across stack frames. And this is all possible because the continuation is now a data structure. We can give that a name, store it for later on, and then call it once, twice, several times. In our first example above, we wound up calling a function with itself. And then in the second example, we wound up calling this let in application 2 times in a row.